All right, so on 290, let's go ahead and take a look at our first example, kind of a free response type question. The rate at which water flows out of a pipe, okay, so we're dealing with water flowing out in gallons per hour, so they do give us some units, is given by a differentiable function. Now, since they use the word differentiable, we can also conclude that we know that this function is also continuous. So no holes, no jumps, no asymptotes, because continuity is a condition for differentiability. So because they use differentiable, we can also know that it's continuous. Time is t. The table below shows the rate as measured every 3 hours for a 24-hour period. Okay, so every 3 hours, they take a look at the rate at which the water is flowing out of the pipe. So they want us to estimate the value of the derivative of this rate, so essentially the rate of a rate, at time 5, and then we're going to use correct units to explain. So in order for us to estimate a derivative, we want to try to pick 2 points, one before the value or the location and then one after. So if we're dealing with time 5, we most likely want to pick these 2 ordered pairs. So r prime of 5 is roughly the slope between r of 6 and r of 3. So doing the change in y's over the change in x's, okay, way back to algebra 1, we'd have 10.8 minus 10.4 over 6 minus 3. So this will give us 0.4 over 2. As a decimal, 0.4 divided by 2. Oh wait, this should be 3. My bad. 0.4 divided by 3. 0.1333. Okay, so 4 decimal places. We're good to go. So this is our derivative value, okay, r prime of 4, but we want to include the units and explain what this means in terms of kind of this scenario of water flowing out of the pipe. So in order for us to figure out the units, we're going to go back to what these numbers actually mean in order to figure out the overall units. So this 10.8 and 10.4 represented gallons per hour, and then we're dividing by another hour unit. So we could write this as gallons per hour per hour. So the division, okay, is essentially taking this unit of measure divided by this unit of measure. Maybe I'll get rid of this line in there so we don't confuse the division in here. So gallons per hour, or some of you might be more familiar with representing this as gallons per hour squared. Okay, if you wanted to multiply by a reciprocal, you'd see how this hour and that hour would combine to get hours squared. So either one of these would be perfectly acceptable. So explain what this means in terms of the rate. So this function r of t represents the rate at which water flows out of a pipe. So the rate at which water flows out of a pipe is increasing or decreasing, since this was a derivative. Now notice how our derivative value was positive, so we'll say is increasing at a rate of this. Okay, 0.13333 gallons per hour. So we're saying that the rate is increasing. Graphically, that would mean that the original function would be concave up. Now notice how this is not an original function. Okay, this is a rate. So this is essentially of a derivative itself, even though they don't label it that way. So if we're taking the derivative of a derivative, notice how we would be representing a second derivative here. That's kind of why we have this hour being squared in terms of the units. So whatever the function represents, the rate at which water flows out of a pipe is increasing or decreasing based off of your value, and then you have the rate itself and then the units of measure. Okay, kind of a throwback question, but this one was a little bit different because the function that we're dealing with was actually a derivative function, even though they didn't essentially label it that way. All right, moving on to B. Using correct units of measure, find the average rate of change of R of t from 3 to 18. So average means the slope between 2 points, okay, specifically your endpoints. So we need r of 3 minus r of 18, those would be your y values, over the change in the x values. So based off the table, r of 3 is 10.4, r of 18, 10.7. 3 minus 8 will have negative 5. So let's go ahead and check this out. Oh wait, this should be 18. So this would be negative 15. At least I caught myself that time. All right, so I got 0.02. 0.02. Now, again, taking a look at the units of measure, the 10.4 and 10.7 represented gallons per hour, and we're dividing by 3 minus 18, which represented hours. So this rate, okay, the average rate of change, actually has the same unit of measure as this derivative rate. Because notice how we're using the same, essentially the same point values from the table. It's just that this is at an instant, whereas this is over time. Okay, average over time. What did you average as the change? So we'll go ahead and say gallons per hour squared. All right, check out C. Is there some time within this interval of the first day from 0 to 24 hours such that the derivative equals 0? Okay, now if we think about our theorems, okay, the intermediate value theorem, the extreme value theorem, Rolle's theorem, mean value theorem, something's kind of going on here. And if they're asking us if the derivative equals 0, of the 4 options, that's kind of cluing us into Rolle's theorem. Okay, do we have a high point or a low point somewhere, or even level? Okay, do we have a slope of 0 at some point? So if we're going to use Rolle's theorem, we have to make sure that we fit the criteria first. So at the top, notice how they do state that r of t is differentiable, and by using that term, we also know that it is continuous. So we can say, since r of t is continuous and differentiable, we also have to check the endpoints for Rolle's theorem. So if we were to check the endpoint at 0 and the endpoint at 24, are they the same? So notice how the table, at the beginning the rate was 9.6, and at the end the rate was also 9.6. So since r of t is continuous and differentiable, with r of 0 equal to r of 24, Rolle's theorem guarantees a value between 0 and 24 such that the derivative of this rate function would be 0. Okay, so that's just Rolle's theorem at a glance, how we have to recognize it, how we have to be familiar with the conditions, and then the conclusion. And notice how the question is there some time? Okay, it's just a yes or no question. They're not asking us to actually find that value. We'd have to have a little bit more information from the table to help us with that. But it's just a yes or no question, and we have to recognize which theorem they're actually talking about.